So before we go into more into hashing, one of the attacks on the hashing is birthday problem. And the birthday problem is as follows. What is the probability that two people in this room have the same month and day of birth? Right? Very high probability. In fact, more than 50% chance that if we did that experiment, everybody told their birthday, we will find that two people have the same birthday. Right? There are 365 days in the year, but there are only 20 people in the room. And the probability can be calculated as follows. If there are two people, the first person will have 365 possibilities, the second person will have 364 possibilities if we want to be different. Right? So the total number of possibilities is 365 square, but these are the different possibilities. So the probability of being same with two people is 1 minus this upon that. That is the probability of two people having the same birthday, which actually turns out to be not very difficult, because if you divide this on that, that is 364 upon 365, and 1 minus that is 1 upon 365. So probability of two people having the same birthday is 1 upon 365. That's easy, right? But what about three people? If you have three people, the total possibilities are 365. If they have to be different, then these many combinations will be different. 365 times 364 times 363. Right? And then if you want to find out what is the probability of same, then you divide this by that and 1 minus something. And you keep doing it for k people. This is the probability of number of different combinations, and this is the total number of combinations. So 1 minus that would be probability of common this one. And this thing actually turns out to be equal to factorial 365 divided by factorial 365 minus k. And this thing is 365 raised to k. So there is a closed form solution for probability of no common day, and then if you do 1 upon 1 minus that, then you get the probability of common day, and that is the probability plotted here. If there are 20 people in the room, 44% chance that we will have common day. 22 people, 51% chance. N people is square root of n. So basically, so the idea is, if you want to find out two people who have the same birthday, you need only square root of 365 people. So how does it apply to hash function? Well, birthday hopefully are random, right? Actually, which they are not. Okay? But assuming that the birthdays are random, actually I'll tell you why they're not random. Two reasons. If you go to countries like India and other places where there is no birth record kept for anybody, if I ask my mom what is her birthday, she doesn't know. And so what happens is when you go to school, everybody is born on July 1st, the opening day of the school. Right? Because he's 5 years old and he has to go into the school. And that's all we know. And and other places, people have argument that when more people are born after the November, are conceived in November, December, winter, this and that. So there are all kinds of stories. Right? So they're not random. But hash function is perfectly random. But to really break it, to find that collision resistance, and then we talk about pre-image resistance, you don't really need to try. If the hash function is 64-bit, you don't really need to try 2 raised to 64. You really need to try only 2 raised to 32. A square root of that, and there's a good chance that you will find it. Good chance. More than 50% chance that you will find it. So that's the whole relationship to birthday problem. Is that when you have a n-bit hash, it is only as strong as n by 2. 2 raised to n by 2. So the probability of hash collisions, what we said actually is right on this slide, that many messages will map to the same. Suppose you have 1000-bit messages. So that way you have 2 raised to 1000 messages. If you have 128-bit hash, then you have only 2 raised to 128 possible hashes. And you will have 2 raised to 1000 by 2 raised to 128. 272 messages will hash to one cell. A large number will go to that cell, right? One table entry. And so how do you find one of those 2 raised to 872? You need to try out a lot. In general, you need to try out 2 raised to n by 2. So now, here you think, suppose you found a way to break MD5 easily. Right? What can you do with it? What kind of mischiefs can you do? And we know that it is used in current world, right? What can you do? Yeah, as long as the hash is same, you can replace a movie X with movie Y, and the torrent system will distribute it all over. Thing is, the system manager, if you're a system manager and you can read the hash for sure, you can just make up a password and then use it. And the system and the computer system will not realize that it's a different password. So there are a lot of things can be done if you break a hash, cryptographic hash. The thing is, John the Ripper is already there though. I mean, John the Ripper does, like it doesn't do any intelligent, it's just brute force search. One could probably come up with something so that, the files can easily be mangled with, and then that will cause havoc in the torrent world. I think we finished everything on the previous slide. 64-bit hash is feasible today, so that's where we don't use it. 128-bit is not feasible today, so that's what we use today. I mean, that is what we talk about possible or not possible. So hash functions use iterative structure. So most of the hash functions are several rounds. Remember DES, 16 rounds. We do the same thing 16 times and it becomes so difficult to break it. So same thing is the hash functions. So they use many rounds. Each round is very simple. You take two values and create a third value. Take two values, create a third value. Take two values, create a third value. So one of the things is the message. You take the message, break into pieces. You take the initial value, IV, initialization value, vector, initialization vector, and then combine them to produce something else, and then, just like we do the cipher text, go to the next, and the final thing is the hash. So this is called the compression function. F is called the compression function. It takes the previous output and the next block to produce the next output. So Merkle proved that if this function f is collision resistant, then this whole structure is collision resistant. So when you design this thing, you just really need to make sure that you analyze this f thoroughly, and if f does not result in collision, then basically collision resistant means it will collide. I mean, basically, if you take 1000 bits and put it into 128-bit, they will collide. But basically, the collision probability is exactly uniform, so that it doesn't just put everything into one place. It puts it uniformly in all the places. All right. So the first hash function would be any encryption scheme, a block cipher. Des would be a hash function, because this would be a des box, and then we just take pieces of the message and keep doing it until at the end. So this is very similar to CBC. CBC was cipher block chaining. So this is the cipher. So H0, you could use initially a value 0 and pad the final block, and then you could compute the encrypted value of HI minus 1. That will give you the cipher text HI. And again, I would have used the letter C rather than H, but anyway, the book uses H. So if you use you keep getting cipher text using the key MI, and then you use the final value as the hash value. Resulting hash is too small. If you use 64-bit, and it can be attacked by the man in the middle, and to meet in the middle. Meet in the middle, if you remember, was that you prepare two tables, and then you prepare half of the table and then one side, and then you prepare the other half, and you see if they match anywhere. So that attack, so basically 64-bit will not be used. So any encryption algorithm that produces 64-bit cannot be used, or should not be used, and so we need bigger things. So NIST produced SHA, which was actually based upon MD5, and MD series is from Ron Rivest. And actually he also has MD6, which he suggested for SHA-3, but then withdrew. So MD6 is not happening. MD5 is the last thing then in that series. Anyway, MD5, similar to MD5, and so the SHA was published in 93 and withdrawn within 2 years, and so SHA-1 is the real one. When today we say SHA, we mean SHA-1. And then 1995 that was published, but again within few years people started thinking that it is weak, and so 2002 SHA-2 had to be published. Now SHA-2 basically has 4 versions: 224, 256, 384 and 512, and SHA-1 is used everywhere in TLS, SSL, PGP, SSH, SMIME and IPsec, and required by law in the United States government applications, and is used in digital signature standard, SHA-1. Now SHA-1 is weak. I mean, now today, for example, in 2011, this is all required, but this is not what you will limit it to. You probably will go with bigger hashes. And the easy thing about the SHA is that you can get the code anywhere on the net. You just look for this pseudocode. It's available. You can write your own program, and then you can go to the NIST for which can check out your implementation and say, yeah, it does it right. So now let's talk about SHA-2. Well, let's talk about SHA-1 first. SHA-1 gives you 160-bit hash using 512-bit blocks and 32-bit operations. So there are few things which change from one SHA to the next, or from one MD to the next MD, and that has how big is the hash, how big is the block, what is the word size, and then the next thing is how many passes, that is the rounds of operations. Basically, so here we have 64, actually I don't know which one to call round here, but maybe we can call it 64 round. Because it has 5 passes of 16 operations, 16 times 80 rounds. In MD4 there were 4 passes, in MD5 there were 4 passes, in MD4 there were 3 passes, so there is 48, 64, now 80. You just make more and more rounds to make it difficult to break. Each block is 512-bit long, and you don't want to use the same thing for very, very long, so basically the maximum limit is 2^64 maximum message size. Before you do 512 bits, you take 512 bits and make 5 times that many bits. Just like we did in DES substitution box, we take 4 bits and we make 6 bits and then we compress it to 4 bits back. Similarly here, we take 512 bits, which in terms of 32-bit word turns out to be 32 times 32 is 1024, so 16 words. 512 bits is 16 words, but we make 80 words out of it. So each word is copied 5 times. So nth word is exclusive R of n-3, n-8, n-14, and n-60th word. So you write only word 1, 2, 3, 4, 5, 6, and then up to 16 you will get right away from the message, and the 17th can be done by this formula. So you get 80 words, and so this was original SHA was simply exclusive of these. In SHA-1, these words are rotated by 1 bit. So each word is rotated by 1 bit. So before exclusive R. So you have total 80 words. So you write down the 80 words here, and then you do some complicated function to get to keep mangling these bits and words. At the end you are left with 160 bits. That's your hash. But as shown here, one of the other things that they do in all of these is that they really don't change most of the words. So A is copied to B position, B is copied to C position, C is copied to D position, D is copied to E position. They're just shifting the words, except that the first word is changed. First word is some complicated function of A, B, C, D, E. So this word changes. Then next time this will shift, and the new word will come in. Then it will shift, and new word will come in. Right? And do this 80 times. All right. So that is SHA-1. And this notation here, left 1, means that shift left, rotate left, rotate left. SHA-2 actually has 4 versions. 256 uses 32-bit operations, 512 uses 64-bit operation, 224 is same as 256, except that you ignore the rest of the bits, and 384 is same as 512, except that you ignore the rest of the bits. So there are 4 versions, and these are the 4 different, these are all the parameters. So for example, 256 will output 256 bits, the internal state will keep 256 bit, the block size is 512 bits, the maximum access size is this much, and the word size is 32, and number of rounds is 64, and so on and so forth. Now this one 2 raised to 63 attack has been done on that SHA-1, which is basically with 160 bit. How much did we expect anyway? How much did we expect the 160 bit hash function? 2 raised to 80 without much difficulty. I mean, that is about the paradox. But they could do it with 17 less, 2 raised to 63. So these have not been broken yet. This table came from Wikipedia. Now let's see what else is here. Matches the key length of 2 key triple dash. So why did they invent 224? When they had 256, why did they invent 224? Because triple dash has 224. Single dash has 56-bit key. Double dash will have 112. Triple dash will have 112. But if you have 2 key triple dash, you will have 112. So 224 divided by 2 is probably 112. So basically it has the same strength as 2 key triple dash. If you remember, triple dash has EDE sequence, and you just use the same key twice. So you have 2 keys, each of them is 56-bit long, and so it takes, in the case of dash, to break dash it requires 2 raised to 112. In case of SHA, it requires 2 raised to 112 for SHA-224. Now we have a little bit more detail of SHA-512. Before I go there, the general description of this is clear, I suppose, is that basically we are going to do something like this in all of these. They are going to put the words in sequence, and then we are going to do some complicated function and put it into different places, and then keep rotating it to 60 to 80 times. So that's what we do here. 512 bit. First we have to make sure that the message is 512 bit or multiple of it, and if it is not, then we append padding bits. So the padding is always 1 followed by zeros, and then the last, at the end we have the length of the whole thing. Length of the, not the whole thing, length of the message. So length of the message is here at the last word, and then rest is all 0 preceded with 1. So the total is 1024, 1024. Then you break it into 1024 bit long, and then you take it through 80 rounds of this kind, where you go through a function with an IB, exclusive OR, and then you go through the function, basically, and so on and so forth. So each of these is 80 rounds, F is 80 rounds, and then when you come out, the result comes out, that goes to the next block, and the result comes out, goes to the next block. So what is this F 80 round thing? This is the complicated function. And so basically you write down A, B, C, D, E, F, G, H. Each of these is 64-bit. Each of these is 64-bit for 500 for SHA-512. So each of these is 64-bit. Then you take A and put it into the B position. Now you take A, B, and C, do the majority bit function on that, and then you exclusive OR with A, and exclusive OR with this, and so on and so forth. So this is basically the diagram which is given here. So all of these functions which are shown in these blocks are described here. So CH is this function, is conditional function EFG. That simply means, and this is bitwise by the way, if E, then select F. If E is 0, then select Z. If E is true, then select F. If E is 0. So you take E, F, and G. Write down bit by bit. So you do this kind of function, that is conditional function, and that will give you some value, and then you exclusive OR with WT, where WT is the TF word. So you had 80 words or whatever number of words in that 512 bit, and let's see how many words we have. So word size is 64, the block size is 1024, so you divide that and that gives you 16. I think from 16 they make 80 anyway. So there are 80 words here, and then so you keep feeding it 1, 2, 3, 4, 5, and that's how the words come in. And then they get in here, and then they go back again and again and again. All right. So this is the conditional function. The next function is majority function, which is here, majority function, which means that this function is true if 2 of the 3 args are true. So you do the same thing, bit by bit. Majority is 0, so you write down 0. Majority is 1, so write down 1. Majority is 1, so write down 1. That function is true if 2 out of the 3 are true. If you were to write down the Boolean method, that would be A and B exclusive or A and C and exclusive or B and C. So that is AB plus AC plus BC. Alright, so now we understand most of the boxes except the sum box. A and B would be 1, A and C would be 1, A and C, B and C would be 1. So let me see. Okay. 1 exclusive or 1 is 0. Alright, so other than summation function, I think they have figured out all of other functions here. These are exclusive or not plus signs. And what is KT? KT is a constant. So they have a table of 80 words which are fixed. Just have to look up into the table and put that word in. So you put 80 words from your message and 80 words from the table. This is how you make the 80 words, by the way. That's also another secret. Is that you take your 1024 bit, which gives you 16 words, 0 through 15 is 16 words, and then you create more words like this. You take W0 from here, W1 from there, W9 from there, W14 from there, take it to these functions, and then exclusive OR that gives you W16. What are these two functions? Sigma 0 and sigma 1 is that rotate by 1 bit x, rotate by 8 bit x, and then shift left. SHR is left shift by n bits. So this should be shift. Anyway, SHR is left shift by n bits and padding 0 on the right. So you do all this shifting and rotating, and that's how you create all these words. So this is very similar to this. There is a lot of complicated stuff being done here, and just to make it as nonlinear and so on and so forth kind of thing, so that you cannot go backwards. To complicate matter, here we have a real addition. This is not exclusive OR. So this plus is a real addition, 64-bit addition. Anyway, I don't expect you to remember any of this detail, except that you should be aware of the complexity and how it is basically. If somebody asks me as to how the SHA-2 works, I will have to go and look it up myself, because I can't remember sigma 1 or sigma 0, rotate left, rotate right, and so on and so forth. I'm not expecting you to remember that. The book actually goes to the extent of showing the whole example worked out from beginning to the end. Just like we did it for AES and DES. I'm not going to subject you to that pain again. Okay. But you have to do it once. So you did for AES. I think for AES you worked out the whole example, and for DES. So I think I just take it for granted that this one, if necessary, you can do it. And if necessary, you can follow the code. So there are programs available on the net. You can just go line by line and see what they are doing. Right? So this is all available as a code, but the book works out the whole example. It takes a message and then takes through all of these steps. All right. So SHA-3. SHA-3 SHA-2 is still working, but the government is NIST is always looking ahead, 5 years ahead. Actually, in this case, maybe even 6 years ahead, because in 2007 they started a competition and they have not finished it yet. So 5 years. 2012, next year, they will announce the competition result. So 2007 they had many of the functions submitted, and as I said, MD6 was one of them, but it has been withdrawn, and has 3 rounds of narrowing down. Every time they take the number of submissions and cut it down. So there are 5 algorithms which were selected last year, December of 2010. 5 algorithms are still candidate. One of those 5 will be announced probably this year, December 2011. They will say, okay, here is the SHA-3. If nothing else, you should be able to distinguish between SHA-256, SHA-512, and SHA-3. So you know that SHA-3 is not the number of bits. In SHA-512 is the 512 is the number of bits, and SHA-512 is actually SHA-2. So that kind of information you should know. But I don't think you can remember these functions. SHA-3 should be a code that can replace SHA-2. So somewhere you are calling this SHA routine, instead of SHA-2 you will be calling SHA-3 routine, and so it should be backward compatible. Process it should be usable online, which means in a software, and evaluation criteria. So it should give you the security close to the maximum size. So if you have 512 bit, it should give you half of that, and 1024 bit should give you half of that. And the time and memory should be as little as possible, and flexibility, simplicity, and everything else. So it's right now it's all requirement and not finally decided. So we don't really know what we'll get. That is the end of this chapter. Basically, we discussed one hash function which was SHA, and so let's see, 5 key points. First point is hash functions can be used to get a digest of a message, and you can make variable size input to produce fixed size, so that it is pseudo random, and then it's very easy to compute. So if we were not looking for cryptographic function, what is the best hash function? CRC. CRC is a very good hash function. If you have simply search application for your table, or you want to make a table or something like that, CRC is a good hash function, and that is used in all Ethernet products today. I mean, in the sense that I published the paper back in 1980s, I think, and that time it was a big news. When you want to have a big table with so many entries, you don't want to, so you want to search it, you just use CRC as a hash. Second thing is, if you want to cryptographic, then you need 3 additional properties, which are, it should be pre-image resistant. Now you got to verify what is pre-image resistant. Means that given H, it is one way, right? Given H, you should not be able to find the message. Second, pre-image resistant means given X, you should not be able to find Y, right? And collision resistant means you should not be able to find any 2 X and Y. You select X, but you cannot find another Y. So X is in your control, even then you cannot find a Y. That is collision resistant. Then we use them for authentication, signatures, and password storage. And SHA-1 produces 160-bit output. SHA-224 produces basically 224-bit output, 256-bit output, and so on and so forth. And they all use 80 rounds. And SHA-3 is not there yet. So basically, just again talking about what has advanced. So last time I taught this course, 2009, we talked mostly about MD5 in big detail. This time we did not go into MD5. It's broken. All right? And maybe next time we will not talk about SHA-1 at all. We will be talking more about SHA-3, and maybe SHA-2 will be, the minimum we will talk about. Homework. So here is the hash function, and this does not use exclusive or, it simply uses a mathematical summation function, a squaring function, and mod function. So you have to find out if it is collision resistant, pre-image resistant, second image resistant, and you have to show the counter example for the property that is not satisfied. If you find one counter example, that's all you need to show. You don't need to try out every possible way and then print out 50-page report. Just one counter example is all you need.